Okay, this problem says a 20-gram ball hangs from the roof of a freight car by a string. Okay, so you'll see that this would be an accelerometer. So you hang a ball from a string, and this will be an accelerometer. If the vehicle is moving at constant velocity, this will hang straight down. And if it's accelerating in this direction, the string will go like that. And the angle will be related to the magnitude of the acceleration. If you accelerate in this direction, the string will hang like that. Okay, so that's the point of the problem. So this is an accelerometer, this is an, okay. When the freight car begins to move, the string makes an angle of 35 degrees. So let's say if it's making an angle of 35 degrees with the vertical, what is the acceleration of the freight car? Okay. And what is the tension in the string? All right, so now what I'll do is I'll just draw the string. This is 35 degrees, okay. So what are the two forces acting on this fella? There's only two forces acting on this sphere: the tension in the string and the weight. Well, and this angle is 35 degrees. And the two forces combined give the object this acceleration. This sphere is accelerating like that. So tension plus weight should equal mass times acceleration. This is Newton's second law. Net force is equal to mass times acceleration. Yep. And you guys see that this guy is accelerating in the x direction. So the y component of the forces cancel, and it's the y component of the tension and y component of the weight cancel. The x component of the tension is what's giving it acceleration. Yep. So we'll write those things down. So the y component is t cosine 35 minus mg equal to 0. Okay, so this is the answer to part B. The tension in the string is 22% greater than the weight of the sphere. Yep. And part A tells you the x component is, this is the x component, which is t sine 35. Is equal to mass times the acceleration. Okay. We just found t, which is 1.22 mg. What does that mean? See, the mass of the sphere is irrelevant. The acceleration only depends on the angle. Okay? The angle tells you the acceleration of the object. Okay? So the acceleration is g. Oops. And okay, all right, actually I'm going to go back just to make sure that I'm going to step back. What I'm going to do is tension is mg divided by that. So Mass cancels, and the acceleration is tan 35 g. So there's the accelerometer. It's tangent of this angle times g is the acceleration. Okay? And so in this case, well, we'll write down what tan 35 is. So 70% of g. Yeah. That's quite a large acceleration. Even a good sports car is probably unable to do that. Yeah. All right, do we understand that? Any questions on that? Okay. This problem says, a roller coaster car starts from rest at the top of a track 30 meters long and inclined at 20 degrees to the horizontal. Assuming friction can be ignored, what is the acceleration of the car? Okay, so I'll represent the car by a point. Okay. There is the weight of the car acting that way. And you saw that this is mg cosine theta. This angle is theta, mg cosine theta. And this is mg sine theta. And there's the normal force. Okay, so there are only two forces acting on the car, the weight and that. This component of the weight is being balanced by the normal force, and this component of the weight is giving an acceleration down the incline. Okay? So if you look at forces in this direction, okay, you can call it whatever you want. So mg cosine theta, mg sine theta is mass times acceleration. The mass cancels. So again, all objects, as long as they're going, there's no friction, they'll be accelerating at g sine theta. And in our problems, theta is 20 degrees, so A is g sine 20. Okay, how much time elapses before it reaches the bottom of the track? So again, we will draw our x-axis this way, and what we want is the distance traveled, and we'll use this formula, x minus x naught is equal to how much time elapses. Okay, so you need a formula that involves t, and we'll use this one. Okay, the initial velocity was 0. So that's 0. We'll say the initial position is 0. That's where the origin is, so this is 0. X is 30 meters. Yeah. Acceleration is 0.34 g t squared. Okay. Yep.
They use that mg sine theta equals to the force.
Mm-hmm. Yeah, that is the force in this direction along that axis. Okay, 30 meters would be an incline from that end of the roof to the bottom. So if you put an ice cube at the top there and it started off at rest, it would take 5 seconds to get to the bottom. This device is called an Atwood's machine. Okay, and this was sort of invented by Mr. Atwood to measure the acceleration due to gravity. We talked about this in the lecture. So back in the old days when you didn't have very good timing devices, it was hard to measure the fall of this guy. Okay. So you needed to slow this thing down. Okay. And this device did that job. So for instance, if you'll see that if this mass is equal to that, you can get it going, it won't accelerate, it'll maintain a constant velocity. Okay? Depending on this mass, you can make the acceleration of this anywhere from 0 to g. Okay? So the device shown below is the Atwood's machine, considered an example 6.5. Assuming that the masses of the string and the frictionless pulley are negligible. So the mass of the string is negligible, the pulley is frictionless, and its mass is also negligible. Its mass is negligible compared to these masses. Okay. What is the assumption that this is frictionless and massless do for you? Why are they telling you that? Okay, so when the mass is negligible, that's when the tension in the string is the same. Okay, if this mass was non-negligible, the tension on either side would be different. Okay, and eventually you will do problems like that. Okay, but for now we keep it simple. The mass is negligible and the tension is the same. Okay. Find an equation for the acceleration of the two blocks. Okay, so we'll set it up with m2 is greater than m1. Okay, and so the magnitude of the acceleration the acceleration points in that direction, and the magnitude is the same. Okay. Okay, these are the two forces acting on this guy. These are the two forces acting on this guy. And we'll write F equal to ma for both these objects. So we have two objects and we'll write two equations. For this object, we'll choose this as the positive direction. So we're using Newton's second law. Okay. So for object 1, T minus m1g equal to m1 times a. For object 2, since he's accelerating that way, we'll choose that as the positive direction. Okay, m2g minus t okay. So there are the two equations, and now find an equation for the acceleration. The two unknowns in the problem are the tension and the acceleration. We know m1 and m2. Okay, so what we'll do is we'll add the two equations. These cancels. So there is the expression for the acceleration in terms of the masses and g. And you can see this from the expression. If the two masses are equal, if m2 is equal to m1, the numerator would be 0, the acceleration would be 0. All right, so if you make the two masses 0, then acceleration is 0. Okay, can I make the acceleration g? I showed you how to make it 0. What is the maximum this acceleration can be? Yeah. So the maximum acceleration you can get is the acceleration due to gravity. Now, how do I make that g?
One of the masses is equal to 0?
Yeah, so if this was not there, this is free falling. Look at that. You make this 0, and then that divided by that is 1, A will equal g. All right, so here is a device. What this did for you is, it lets you make acceleration anywhere from 0 to g. So depending on what mass m1 you put, you can dial the acceleration to anything you want between those limits. You know? And that's what that device is. Okay. So here's the acceleration. Find an equation for the tension in the string. Find both the acceleration and the block. So once you calculate the acceleration, you can plug it in here and do the tension. So tension is m2g okay. All right, so I'll let you guys put in these numbers, find the acceleration and tension if the block masses are 2 and 4 kg. Okay, I'll let you do that. So this would be 2 divided by 6. For these masses, the acceleration would be 2 divided by 6, 1/3 g. Okay. So if one mass is double the other mass, the acceleration is 1/3 g. Okay. All right, so this was the Atwood's machine. Okay, now we'll make this problem slightly more complicated. Okay, so here's that problem, except that we'll put this guy on an incline. Do you guys see any relationship between this guy and this guy? Okay, what is the relationship?
They're still connected by a pulley, but now one's on an incline, so it would make the heavier one fall stupid slower.
Okay. So if this guy, well, this is frictionless. If this incline became 90 degrees, that would become this problem. Okay. So in the limit, this angle goes to 90 degrees, it becomes the Atwood's machine problem. Okay. All right. So a 2 kg block and a 4 kg block, same masses again, are connected by a light string as shown. That angle is theta, friction is negligible. What is the acceleration of the block and the tension in the string? Well, they didn't mention that the pulley is massless. We'll have to assume pulley is massless, because right now all we know to do is when the tensions are equal. Okay. And also, if the pulley did have mass, they would have to give us the mass. And since they didn't give us the mass, we'll assume it's massless. You know? All right. So, okay, what is relevant is this guy is not useful. His components along the incline and perpendicular to the incline are useful. and this is m1g cosine theta, which is balanced by the normal force. All right, so when this guy is on an incline, if this guy is heavier than him, this will accelerate that way. But you can make it accelerate this way if this guy is heavier than him, but he'll have to be a little more heavier than just heavier. Okay, so we won't get into that. So right now, this guy is heavier, so he'll accelerate like that. Okay. So we'll write the motion of this guy along that direction. The two forces in that direction are the tension and that. So tension minus m1g sine theta equal to m1 times a. For this guy, we'll choose this direction as positive. The two forces are m2g minus tension. Okay. You add the two equations. That will cancel. And what you get is m2 minus m1 sine theta g equal to m1 plus m2 a. See, this expression is very similar to that expression. The only difference was you had a factor of sine theta there. And we did tell you that if you make theta 90 degrees, this would become 1, and that expression would reduce to that. Okay? All right, so this is a more general problem. All right, what is the acceleration of each block? The tension in the string. So there's the acceleration, and the tension is, of course, m1 times g sine theta plus a. Okay, so you put in the numbers there, calculate acceleration, put in the acceleration here, and calculate the tension. Okay? You guys understand that? Yeah. All right, so a contestant in a winter sporting event pushes a 45 kg block of ice across a frozen lake as shown below. Calculate the minimum force he must exert to get the block moving. Okay. So the minimum force would be, okay. So what you want is a force, the x component of the minimum force should equal the maximum static friction force to get it moving. Okay. So let's say this is minimum. F min cosine 25 should equal the maximum static friction force. Okay. So F min well, what is the static friction force? A maximum static friction force, it's mu s times the normal force. Well, let's look at what is the normal force. There's the weight, mg, and you see F min sine 25 is also acting downwards. So the normal force has to balance those two forces. So the normal force is equal to F min sine 25 plus mg. Okay. So we're going to plug all of that in. Okay. And actually I'll write this as theta, so we'll have general expressions. Theta. Okay. So F min cosine theta equal to mu s times F min sine theta plus mg. Okay, so what we are solving for is F min. I'll bring this on this side. Okay. F min cosine theta plus mu s sine theta is equal to mu s times mg. F min works out to mu s mg divided by cosine theta plus mu s sine theta.
On the bottom it says cosine theta plus mu s sine theta.
Oh, minus. When this term comes over there, it becomes minus. All right. So here's a couple of things you can test. So when you do calculations like this, you want to see if it has the right limit. Okay, so when theta is 0, when you're pushing horizontally, when theta is 0, this is 1, this term is 0, and the minimum force is just mu s times the normal force equal to the mg. Okay, so it has the right limit. All right, so let's now we'll put the 25 degrees in there. Okay. So there's the minimum force. Okay, so again, let me remind you, if you were pushing it with a horizontal force, F min would have to be Fs max. F min would be just mu s times mg. Okay, for that case, for that simple case. So now that you're pushing downwards on it, your effective static coefficient of friction has increased. Okay. Yeah. So this is a number less than 1. Okay. Can you increase this angle and keep pushing that? Pushing it forward. So let's say, for instance, if that angle were 90 degrees, of course it wouldn't move forward, right? So what would be the critical angle at which it would not move forward? When this guy goes negative, then you can't push it. Right? So you guys understand? So you can solve for an angle theta, critical angle above which you can't push it forward. Okay. So, and what is the acceleration once it starts to move? So once you start it moving, then what you could, you can calculate the x component. You would, for calculate F min, and then you'd have to replace by mu k. The friction force would decrease. This is the maximum static friction force. Once it starts moving, the friction force would decrease, and this x component will make the object accelerate. Okay. Do you want me to put numbers in the problem? I want to solve 2 other problems and then get on to chapter 9. Do you want me to put numbers there, or you guys understand this?
Maybe some numbers, please.
All right. Okay, so we need ice on ice. So let's look up mu s and mu k for ice on ice. All right. So for ice on ice, mu s is 0.05 and mu k is point. All right, so let's do this. So there's that. So I'm going to calculate okay, so mu s is 0.05. So what I'm going to do is I'm just going to calculate the denominator and then do that first. You'll see why I'm doing that. So when you were pushing down at an angle of 25 degrees, what does mu_s measure? It measures the stickiness of the two surfaces. So when you're pushing down, you made it stickier by that percent. You increased the stickiness by 8%. Yeah, that's what you did. All right, now we'll put in the numbers. 1.08 into 0.05. So the minimum force, that's the magnitude of the minimum force. Okay, we'll keep that. That's okay. Now part B says, what is the acceleration once it starts to move if the force is maintained? Okay, so now part B, you're applying a force. This minimum force is 0.054 mg. This angle is 25 degrees. Okay, there's the y component of the minimum force. The weight, the normal force, is equal to the sum of the two. Okay, so F min cosine 25 minus Fk equal to mass times the acceleration. Okay, the force along the x-axis is this force minus that. Okay, and the kinetic friction force is mu k times the normal force, which is that. All right. And so you can solve for the acceleration. Now actually I'll put in the F min there. F min is that. And mu k was 0.035, so 0.054 mg cosine 25 minus 0.03 mg plus 0.054 mg sine 25 equal to mass times the acceleration. And you see the mass will cancel. Well, again, the and G is common, so that'll be the acceleration of the object. Okay. So it takes a larger force to get it started, but once it's started, if you apply the same force, it'll accelerate because the kinetic friction force is smaller. Okay? Okay, I'll solve this one more problem and then we'll take a 5-minute break. Okay, this says calculate the velocity of a spherical raindrop would achieve falling from 5 kilometers. So 5 kilometers is roughly the height. Well, so that's a high cloud. Okay, so if rain fell from there, and if there was no drag forces, at what speed would the raindrop hit the ground? Okay. Now, the acceleration would be g, okay, and we'll make x point that way. So v square would equal v naught square plus 2a x minus x naught. Okay. So our axis is pointing that way. Final x position minus initial x position, that's 5 kilometers. Acceleration is g. Initial velocity is 0. Okay. So the speed at which the raindrop would hit is 2g x minus x naught. And 5 kilometers is 5,000 meters. So if there were no drag forces on a raindrop that fell from 5 kilometers up, it would be going at 313 meters per second. The speed of sound is 340 meters per second, almost at Mach 1, which is about 750 miles an hour. You certainly wouldn't be walking in rain. Okay. It would be raining bullets. So obviously the drag forces are a good thing here. Okay. With air drag, let's find out what would be the speed. Okay. With drag forces present, okay, what is happening is as it's falling faster, the drag force is increasing. And so you reach terminal velocity when this drag force is equal to the weight. Okay. So you reach terminal velocity fairly quickly. And so the drag forces, okay, so they tell you with air drag, take the size across the drop to be 4 millimeters. So the drop is about that big, half a centimeter. So the diameter of the drop is 4 millimeters. The density of water is that, and the surface area to be, again, we don't want all of that. So here's the expression for the drag force. Okay. There's the expression for the drag force. And the terminal velocity is given by that. Okay. So the terminal velocity is 2 mg. Okay. This is the weight of the raindrop. This is the drag coefficient, which they haven't given, so we'll assume it to be about half. This is the density of the fluid through which you're falling. What is the raindrop falling through? Air. Okay, and this is the area of cross section of the raindrop. Okay, so that is area. Okay, so the terminal velocity is the mass of the raindrop is the density of water times the volume of the spherical drop. C is and air times pi r squared. Okay, area of cross section. Two 8/3 density of water R G C air. All right, so now we can put all these numbers in. 8/3 density of water is 1,000 kg per meter cube. The radius of the drop was 2 millimeters. 9.8 is G. C will take to be half, and the density of air is about 1.3. At ground level, it's 1.3. At 5 kilometers, it's roughly 60 or 70%, but we're not going to account for the variation in density. So at higher levels, the drag forces are less because the density is lower. But we won't worry about that. Okay, there's the numbers. Okay, so this is killed by that. So what you're left with is 16 into 9.8 divided by 3 into 0.5 into 1.3. Okay, that is a much better velocity to walk in than that. Yeah. Much safer, certainly. All right, guys, so